All right, so today we're going to be talking about future values of annuities. Now, if you don't know what an annuity is, an annuity is a financial plan characterized by regular payments. We can view an annuity as a savings plan in which the regular payments are contributions to the account. Then we can ask what the total value of the account will become. Also, we can view an annuity as a payment plan, such as for retirement, in which regular payments are made from an account, often to an individual. For the purposes of this class, we will deal with annuities that have payments that begin and end on fixed dates. So let's see a specific type of annuity. So an ordinary annuity is an annuity in which payments are made at the end of each of the equal payment intervals. So let's see an example of that. Example 1 says, suppose you invested $100 at the end of each year for 5 years in an account that paid interest at 10% compounded annually. How much money would you have in the account at the end of 5 years? So I'm going to draw a little timeline here. So that is the starting point. And then after 1 year, you will have invested $100. And then at the end of 2 years, you will have invested another $100. And at the end of the 5th year, you will also have invested another $100. However, because we have an account where 10% is being compounded annually, what's going to happen to this first $100 is that it will gain 10% interest until the end of the 5 years. So it'll gain 10% here, it'll gain 10% here, 10% here, and 10% here at the end of the 5th year. So the way that that $100 will have accumulated, we can think about it as 100 times the 10% interest 4 times. Now this next $100, it is not sitting in the account for as long, and it will only have accumulated interest 3 times. So it would be 100 times 1.10 to the third power. And we are going to follow this pattern. So that at the end of the 3rd year, that will have sat in your account and gained interest twice. And if we wanted, we could write this last one as 100 times 1.10 to the 0 power, but anything to the 0 power is just 1, so I'm maybe going to leave that as that. And so the future value of the account is just going to be the sum of all of these 5 terms. So I'm going to abbreviate future value as FV. The future value of this account will be 100 plus 100 times 1.10 to the first power plus 100 times 1.10 to the second power until we get to the last term, which is 100 times 1.10 to the 4th power. Hopefully this should look familiar to you. If it doesn't, go back and watch the video on sequences and the sum of geometric sequences. So just as a little refresher, if you are trying to find the sum of the first n terms of a sequence, that is equal to whatever your first term is times 1 minus the common ratio raised to the power of n, where again n is the number of terms in the sequence, divided by 1 minus the common ratio. So if we were to apply that formula here, we would get that the future value is equal to 100 times 1 minus the common ratio, which is 1.10, and we want to raise that to the 5th power since there are 5 terms that we're adding up, over 1 minus 1.10. So I'm going to go ahead and throw that into my calculator. So I went ahead and threw that expression into my calculator, and so at the end of the 5-year period, in our account, we will have $610.51. So let's look at this formula that I had written right here. That was to find the future value for that annuity that was described up above. And I want to take this and use it to generalize a general formula. So whatever amount that you start off with, let's say it's equal to R, or sorry, R would represent like the regular payments, which in this case is $100, but in general, let's call it R. And then we would have times 1 minus 1 plus the annual interest rate raised to the power. In our previous example, it was 5, but in general, let's just call it n, and then divide that by 1 minus the quantity 1 plus I. And again, our annual interest rate in the above example was 10%, so I would be 0.10. But we can actually simplify this. So if I distribute the negative sign here, then our new denominator would be 1 minus 1 minus I. And so the ones would disappear. And so in the bottom, we would just be left with negative I. Now, if I factored out a negative 1 from the numerator, what we could do is we could have this be negative R times, if I factored out a negative 1 from the numerator, then we could rewrite that as 1 plus I to the nth power minus 1 all over negative I, and then this negative and this negative would cancel each other out, and so we would be left with this thing here. Sorry if that was a little convoluted, but anyway, so let's talk about the future value of an ordinary annuity. So if $R is deposited at the end of each period for n periods in an annuity that earns interest at a rate of I per period, the future value of the annuity will be given by that equation. And I've tried to kind of generalize where we get that equation from, but this is the important part. So now that we have this very nice formula, we don't have to go and draw that weird timeline thing and do all that nonsense. We can just utilize the formula that we've derived here. So example 2 says, Mr. Kwan invests $2,000 at the end of each year for 36 years until age 65 in an account that pays 10% compounded annually. How much does Mr. Kwan have at age 65? So your textbook denotes the future value as S, so I'm going to try to be consistent with that. So the future value of this ordinary annuity is going to equal the R value, which is the regular payments. So that would be 2,000. And we are going to multiply that by 1 plus the interest rate. So here it's compounded annually, so we don't need to do any division. So we could just write our interest rate as 0.10. And the number, our n value, the number of terms would be 36, since we're compounding for 36 years, minus 1 over 0.10. Okay, so I went ahead and I threw that into my calculator, and basically the point of this problem is to show that Mr. Kwan is going to come out with a lot of money. So at the end of the 36 years, he will have $598,254.